Here is the answer for the day 4 Bellwork. Balance the double replacement reaction. On the reactant side, we have potassium hydroxide dissolved in water. It combines with hydrogen phosphate, which is dissolved in water, and that produces potassium phosphate, which is dissolved in water, plus H2O, liquid, so liquid water. This is a double replacement reaction because we're starting with two aqueous solutions, and it's creating an aqueous solution plus something else that's not an aqueous solution. It could be a solid, a liquid, or a gas. In this case, the other thing is a liquid. Double replacement refers to the cations switching positions. The potassium cation and the hydrogen cations are going to switch positions. The potassium is going to bond with the phosphate, and the hydrogen is going to bond with the hydroxide. So this is all written out. We just need to balance it by doing the coefficients. There's one capital K here, but on this side, 3 capital Ks. So let's put a 3 in front. That makes 3 OHs, or 3 hydroxides. On the other side, we need to have 3 hydroxides. But it's a little confusing to see any OHs when water is written in this format. Remember that the other way to write H2O is in its ionic formula version, HOH. It's the same thing, it's still H2O, but it just is a little easier to see. Here is a hydrogen ion with a positive 1 charge, and here is a hydroxide ion with a negative 1 charge. So if there's a 3 here, that's 3 OHs, then we would want to have a 3 here, right, to have 3 OHs. We want to have a 3 in front of that water. All right, on this side there are 3 hydrogens, and when we put that 3 in front of the water, did that take care of the 3 hydrogens? Look at that alternate version. That's 3 H's right there. Okay, then there is 1 phosphate, and on this side there's 1 phosphate. When I see PO4 with my eyes, I don't separately see a P and an O4. My eyes see it together and call it phosphate. So this is balanced. This thing that we wrote up here, you might erase that off. That's not actually part of the final answer. It was just something we did to help us see the hydrogens and the hydroxides. Okay, question B. Complete the double replacement formula and then balance it. So we have silver nitrate, aqueous, plus sodium chloride, aqueous, produces silver chloride solid plus, and then this one's missing. But I do know it's going to be aqueous. So if this is double replacement, then the silver cation and the sodium cation are switching positions. The silver gets bonded with the chloride. That's already written here. What's the sodium get bonded to? It gets bonded to the nitrate. So on this line we have sodium nitrate. Now don't just write NaNO3 and think you're done. You got to think about charges. The charge on sodium is positive 1 because it's in group 1A. The charge on nitrate is negative 1 from the page 268 chart. These do balance each other, so NaNO3 is the correct formula for sodium nitrate. Remember how this other one is going to be aqueous. It's going to still be ions that are dissolved in water. Okay, now that we have that, we can do our coefficients. There's 1 Ag, on this side 1 Ag. There's 1 NO3, and over here there's 1 NO3. There's 1 Na, and here there's 1 Na. And there's 1 Cl, and here there's 1 Cl. This is all balanced out. Question C. Potassium iodide, aqueous, plus some reactant, produces potassium nitrate, aqueous, plus lead iodide, solid. This has the format of a double replacement if this piece here is something that is aqueous. What do you think it needs to be? Well, I see the K, and here I see the K, and here I see an I, and here I see an I, but like what don't we have yet on the left side? We don't have the nitrate, and we don't have the lead. So I think this missing piece is lead nitrate. So Pb, NO3. But it's not as easy as that. You've got to think about charges in case you need subscripts on these. So let's think about the charges. Nitrate is a -1 charge. You can get that from page 268. You might remember from question B how we had nitrate, it was -1. Or you can even get it from right here. Because if potassium's in group 1, then potassium's a +1, so I guess the nitrate that goes with it is -1. What charge is the Pb? That's lead. That's one of those transition metals, and it has more than one possible charge. So what kind of lead do we have in this problem? Well, let's look right here to see what kind of lead we have. What is the charge on iodide, which is in group 7A? One iodide has a -1 charge, and this has two iodides. So 2 times -1 is a -2 charge. If this portion is -2, then what's the charge on the Pb that balances with that? That's got to be +2. Our lead is the kind of lead with a +2 charge. It's called lead 2. So the formula can't be PbNO3. We need parentheses around this and then a 2 here to make the correct formula. Now, none of the charges that we wrote down were actually part of the equation. So after doing those for work, you might erase those out of there just so they're not cluttering things up. Now let's do our coefficients. There's one capital K, there's one capital K. There's one I, but over here there are two I's. So we need a 2 here. But now that makes 2 K's. So we need a 2 here. As soon as you put the 2 here, that's 2 nitrates. Well, that's a good thing because on this side we have 2 nitrates. There's 1 Pb, and on this side there's 1 Pb. Now it's all balanced. I notice I didn't write anything in parentheses to say solid, liquid, gas, or aqueous. What does this need to be right here? This is aqueous. Double replacement reactions occur when 2 aqueous solutions are mixed together. So both of the things on the left side, they both have to be aqueous to be double replacement. Okay, question D. Barium nitrate aqueous plus hydrogen sulfate aqueous produces, and then this entire side is blank. But we are told this is double replacement. So think about what happens. The barium and the hydrogen are going to switch positions. What's the barium going to bond to? It's going to bond to the sulfate, making barium sulfate. So BaSO4. Let's check if that's the right formula. Barium is in group 2A, so it's a +2 ion. Sulfate is a -2 ion from page 268. Those balance each other just having one of each. So BaSO4 is the correct formula. And that's going to be a solid. You might not know that, but we actually are going to do a few different experiments this year where we create barium sulfate. You'll see that it is, in fact, a solid product. What is the other part to the products? Well, we don't have nitrate over on this side yet, and we don't have the hydrogen over there. So if you have hydrogen and nitrate and you combine them together, what do you get? You get hydrogen nitrate. So HNO3. Now, put some thought into the charges. Don't just assume that it's HNO3 and you're done. What's the charge on hydrogen? It's group 1A, so it's +1. What's the charge on nitrate? It's -1. It says that on page 268. Those match each other, so HNO3 actually is the right formula for hydrogen nitrate. This one is going to be aqueous. You might not know that until we actually do some lab experiments, but what you'll discover this year is that almost everything that has nitrate in it dissolves in water, and so the result is an aqueous solution. Now that we've written out the skeleton equation, let's balance it. There's 1 barium, 1 barium. There's 2 nitrates, but on this side there's only 1 nitrate, so we need a 2 in front. That makes 2 H's, but that's okay because there's 2 H's. And then there is a single SO4 here, and there's a single SO4 here, so the sulfates are balanced too.